Dingo happy beeps. Hey, how's everybody doing today?
Not too bad, how much yourself?
Doing okay. So, apologies if the audio quality is a little bit off. I'm on a different setup right now.
It actually sounds pretty good.
Okay, cool. Alright, I will screenshot the 4 people who are here on time. There's like unspecified rewards in the future. Alright, cool. Well, this is our last class. And it's my last class for the quarter, but it's our last 222 class. So, let's see, a few things. First of all, SLP presentations, really nice work, everybody. So those looked really good. We had a number of visitors come in, and they seemed to enjoy what they saw and heard, and they thought there were some interesting projects going on. So that's all really good. I think that was a big success. I did not get to see as many projects as I wanted to. I only made it into a few rooms. I was taking turns with Izad. But what I saw looked really awesome. So really nice job with the SLP presentations.
Yeah, I think I kind of liked the whole process because it was nice to see what other people were doing.
Definitely.
You know, it kind of makes you feel good that, you know, it's like, oh, okay, I'm doing something still within the realm that everybody else is kind of working in. So
yeah. I mean, it's kind of it's a hard project to tackle in a vacuum, but it's nice when you can see other projects and sort of realize other people are in the same boat. And some people have made more progress, some people have made less progress, but it's really about learning, right? If you're learning some new stuff and trying some new things and you know, making some kind of progress, even if it feels like it's backwards sometime, that's all like good experience. And it's all part of what we're hoping you get out of tackling, you know, a year-long project like this. So
I was actually in a group with another person making a Unity game, and some of the features that he was showing me were really cool because I didn't even know they existed.
Oh, nice.
Stuff that I might implement in my game.
That's awesome.
So cool to learn that too.
Yeah, it's nice when you get some interaction with other students, and sometimes, you know, people will ask you a question and it can send you in a totally new direction, or can show you something they're doing and that can like open up a whole new idea for you. I've had cases where students found out they were working on something very similar to someone else and they ended up collaborating after that. There's all kinds of things that can happen. It's also a really good opportunity to kind of work on your elevator pitch. And how many people here know what I mean by an elevator pitch? So this is you know, imagine that you're you know, somewhere in a city and you get on an elevator, and as the door is closing, you know, someone sticks their hand in to catch the door and they walk in, and it's someone like, you know, Bill Gates or Jeff Bezos, you know, or someone like that. Somebody who you know, most people never get an opportunity to see in real life, and now you've got them as a captive audience for however long you're in the elevator together, which is typically going to be, you know, about 30 seconds. And so if you've got some idea, some project that you want to do, the question is, how would you describe this to someone in 30 seconds in a way that, you know, might get you contact information, or they might get out and say, you know, tell me more about this or something like that. So take a project that you've been working on maybe for, you know, a number of months, maybe you've been thinking about it for years, and you've got 30 seconds to describe it in a way which captures someone's attention, right? That's an elevator pitch. And that's a good thing that you can develop by talking to people about what you're doing. And until you really kind of have conversations with other people, you're sort of like, you know, trapped in your own head most of the time with what you're working on. And a few conversations can really kind of help you reframe an idea or a project. And I think that's a really useful benefit of presenting your work. And so that's something else that can come from SLPs. Any other comments or thoughts or feedback on SLP presentations? And so somebody just posted a link in chat to a web page they put together to highlight their projects, and this is a really good thing to do, right? To be able to document things that you're working on, or maybe things that you're just thinking about, and it's pretty available to do these days, right? You don't need to like learn web development. You don't need to host a server somewhere, right? So this person is using GitHub, and you can go to GitHub or GitLab, and there's a markdown language you can use for readmes and such, and you can put a whole project there, a whole collection of projects. You can go to sites like Hackaday, and you can talk about your projects there and put in links and pictures. And people will contact you sometimes about this and ask you questions about it. And it's, these are all ways you can sort of get your ideas out there. And usually if you start bouncing ideas off other people, that can become a really rich source of new ideas, right? Fresh ideas. It's also useful when you're applying for a job or a position somewhere, to have something like one website you can just point someone to, and they can look up and they can see what you've been doing and what kinds of things you're interested in, some things that your skill set has made possible, and so on and so forth. Alright, so yeah, good job with the SLPs, and between now and June, hopefully you can continue developing your projects towards, a first or more complete prototype. And then in June, there's a bigger expo where, all of the 223 students and all of these odd students will get together and present. That will hopefully be an in-person presentation, at least for the in-person classes. And that, we typically have people from other parts of the school, or people from outside, from industry and such, coming in to talk to students and see what they're doing. And it's usually a pretty good affair and interesting for everyone. All right, PA5. So PA5 is graded. I graded it Tuesday and Wednesday and posted grades with feedback. And everything that was submitted as of this morning at 8, I believe I've graded and given feedback to. And PA5 looked good. There were sort of three main pieces to it. The first piece was just trying to get the maximum value out of a function, and most people were able to do that successfully. The second piece was the dynamic programming, and the majority of people got the dynamic programming working, and that's really adding, something in the beginning and end of your function. In the beginning, you look for a saved value. At the end, you save your value if you had to calculate it. And then the third piece was the item count, and the item count is sort of the trickiest part. And it's a matter of, as you're looking for a best solution, you need to remember not just the best value so far, but also the best count of items that got you that value so far. And most people made at least, a really close attempt on that if they didn't get all the way there. It's looked like mostly small things that needed to be worked out, like initializing your item count array in the beginning, or maybe being off by one in an index, or things like that. All right, so so PA5, if you don't understand dynamic programming, if you don't understand these recursive substructure type problems and so on. We've got 1 more hour of office hours tomorrow morning at 9 o'clock. Come by and ask then, or ask in class right now, right? We got about 2 hours in class today, and I'm really just planning to do some wrap up on heaps and then kind of talk about the final exam and kind of review the whole quarter. But if you have questions, this is a good time and place to ask them.
I have one question.
Mm-hmm.
Do you think you could maybe post in the shared code the greatest common substring algorithm you showed us, that cached stuff?
Yeah.
That one still mystifies me a little bit, but I'd really like to just like sit down and have a look at it for a while, if at all possible.
Let's see what we got. So I think that was LCS 3.
Could you also maybe post the one that doesn't cache, so I can kind of compare the differences between the two?
Well, you can remove the caching pretty easily by just getting rid of this. Just get rid of this. Right. So we always need to index the cache somehow. The goal is, if you're calling a function blah with some arguments, we need to know if you've called this function with these arguments before. So we need to somehow use these arguments to access a cache of saved results and know whether or not we've saved something in there or not. So for longest common subsequence, it turns out, since we're always truncating the strings, the length of the two arguments uniquely identifies a pair of values that we called this function with. And so I actually chose to use the length of the two strings as the index into a two-dimensional save array. And so if that's not null, then I go ahead and return it. And what I'm saving in that array is the longest common substring. So it's a cache of car stars.
This would probably be a good spot to use a hash table.
You could use a hash table, definitely. And in general, if you didn't know something peculiar about the arguments that you could use as an index, you could just use a big hash. And that would be a great application for a hash table. And then at the end, before doing a return, this stuff happens. So space is made for an entry in the cache, and then you string copy the return string. And I just blindly made it, 100 characters. But yeah, I can pop this over. So that should be on there under LCS.
Sweet.
Yeah.
Thank you.
Mm-hmm. The other problem that we did not talk about was the egg drop problem, and that's a fun problem, but we ran out of time for it. But maybe we'll talk about it in 223. But the question with the egg drop is, you're trying to determine what the highest floor of a building is that you can drop an egg from without it breaking. And if you only have one egg, you have to start from the first floor, the second, the third, work your way up until it breaks, and then you've got your answer. But if you have two eggs, you can do a little better than that. You could make your first drop, say halfway up the building. And if it happens to survive, then you only have to go, determine a floor from there up to the top of the building. And you still have two eggs. If it happens to crack when you drop it from the halfway point, now you can explore the lower half with one egg. And it's going to take you fewer tries in general. And so the question is, if you have a certain number of eggs and a certain number of floors, what's the guaranteed fewest number of trials that you need to find the floor where the egg first breaks? And there's a way to think of this as something with recursive substructure.
Would that be log of n?
It's not that straightforward, but that's what it feels like at first. But it's different because if the egg survives, you've got 2 eggs left to work with for the upper half of the building. If the egg breaks, you've only got 1 egg left to work on the lower half. And so it's not a straight divide in half each time. Sometimes you divide the problem in half or some other chunk, and you haven't lost anything. You still have all your eggs. So it's a
kind of like divide it in half and play it safe for the other one if it doesn't work, kind of deal. So it can be complex.
And if it survives, then you've got 2 eggs left. So maybe you'll start it from a lower floor, lower than halfway up, right? So that there's a better chance it survives. And if you've only cut it in a third, but you've got 2 eggs left, that may take you less time. And so the analysis is one story, but the recursive structure of it is very straightforward, and it's like longest common subsequence or knapsack. You can basically break it into a series of other calls to this function with smaller values, and you combine the results from those calls, and you can answer the original question. So yeah, there's a whole bunch of problems like that, and you can find a number of these online, and they're fun to play with.
And 223, is that going to be all Java related?
223 is all Java, so it's object-oriented programming. We might do a little C++ at some point, but it's pretty much all Java.
Okay, for some reason I was thinking it was like advanced stuff going further into data structures. But
it is, so it's advanced data structures in Java. So we do 2 things. We learn object-oriented programming, and then we go further with data structures. And to go further with data structures, right, it's nice to not have to reinvent the wheel every time you want to roll somewhere. So there's classes in Java for things like hash tables and collections, things like linked lists and so on, and we can just use those to give us access to these data structures. We can also create our own data structures, like a decision tree, for example, but in an object-oriented realm, it's a lot easier, and it comes out a lot more natural than it does in something like C. So yeah, we'll definitely be continuing data structures, but we'll be doing it in Java.
Okay. Yeah. Yeah, it's nice to just say that this equals a new, array list or, priority queue.
Yeah, using new instead of like malloc and looping and all this kind of stuff is definitely nice.
No directly touching pointers, you just have, like a reference.
Yeah, there's very deliberately no pointers, although you sometimes get null pointer exceptions, but you very definitely don't have, memory addresses that you manipulate. You don't do mallocs and frees and things like that. There's a garbage collector that reclaims memory when it's not being used anymore. And so there's all these things that make life just sort of a whole lot easier, and will probably make us lazy in good ways.
Yeah, it'll be nice to learn the basics of Java.
Yeah.
I want to see how it contrasts to C#.
Yeah, I do not know a lot of C#. I've never developed anything in it, so but my understanding is it's kind of like Microsoft's version of Java, so that would be an interesting comparison.
Yeah, I think the main methods are a little different and how some of the stuff is declared, but Java is, I don't know, Java seems like it'd be more specifying on a certain object, where C# is more, I don't know.
Mm-hmm.
I guess I have to think about it a little bit more, but C# is definitely a little bit.
I hear the differences really come in when you start talking about generics.
Ah, okay. Interesting. And we will talk some about generics in Java, so you'll probably see that difference then. All right, so PA5, yeah, if you've got questions about it, let's keep talking about it, or come by office hours. But like I say, by and large, it looked like people were pretty much on the right track and got most of the way there, if not completely. All right, so let's talk about implementing heaps. We were talking about heaps on Tuesday, and the only topic we did not get to is how do we write code to implement a heap. So as a refresher, a heap is something that has, a heap structure. So it's structured or shaped like a heap. Every level is full except for the deepest level, which has to be filled in from left to right. And each node satisfies a heap property. So for a min heap, this means each node is smaller than both of its children. For a max heap, it means each node is bigger than both of its children. So a heap is a binary tree that satisfies those properties. Go ahead.
Can I ask why we specify it as a tree or a heap? Is it just basically due to balance? Is that really what we're looking for?
So a heap is a tree. So a tree is the most general notion. A heap is a particular type of tree. So is a binary search tree. But they're different types. So it's like, here's a tree, here's a binary tree, here's a binary search tree, here's a heap. There's a tree of tree types. They're both binary trees, but they have very different properties. For example, right, this is a perfectly fine min heap. It's a horrible binary search tree. Because, we've got something bigger than the root on both sides of it. That's not a BST. But this is a min heap because the root node is smaller than both children. This is a binary search tree. It's not a heap because this node violates the heap property. This is not a binary search tree, or because this thing is bigger than the root. It's also not a heap because it doesn't have the shape of a heap. It also violates it satisfies the min heap property here, so it's got the min heap property everywhere, but it doesn't have the shape of a heap. So trees and binary trees are general things. There's no particular requirements on them with respect to the value of a node versus its parent or its children. But binary search trees and heaps have these requirements on them.
Okay, that makes more sense. Thank
Okay. So when we have a heap, right, if we want to add something to a heap, we need to insert it into what I can think of as the last position in the heap, or right after the last position in the heap. And when we want to pull off, the largest or smallest from a max heap or a min heap, this is the first, or the root node of the heap. And we're used to getting to the root. That's usually our handle to our tree-like structure. But getting to this last node is a tricky business, right? Because if my heap looks like this, my last node is what I get to from the root going to the right. But if my heap looks like this, I have to start from the root and go left, left, left. Or if my heap looks like this, I have to start from the root and go left and then right and then left. And so there's no clear traversal algorithm that will quickly get us to the last node of our heap. And if we want to remove the root of the heap, what we do is we pop off the root value, we take that last node, we move it to the heap, and then we down heap. We compare it to its children to see if it satisfies the heap property, and we keep moving down until we've satisfied the heap property. And so a regular structure like we've been using for trees, where we have a node and a left child and a right child, does not really work well for heaps. Right? We would have to explore every node to figure out where the last node is and to remove it and so on and so forth. But it turns out there's a totally different way to implement a heap in a program, and that's with an array. just a plain old array. And if we think of our heaps as having numbers in them, integers, we can just use an array of integers. And so here's what we're going to do. We're going to make an array. And so on. And when we want to build our heap, we're just going to start off, with the root node, move across each level, and when we get to the end of one level, come down to a deeper level. And as we go through the nodes in that order, we're going to use consecutive locations in our array to store them. But we're going to skip index 0. We're just going to waste that one spot in our array. And so our heap is going to look like this, and I'm going to draw index values. Thank you so much.
You're very welcome.
I'm just going to draw indexes in place of the actual data values. And so here's a heap that has 9 elements in it. And so in addition to this array, which I could think of as heap, I could have a variable like heap size. And I would set that equal to 9 to say, hey, I got 9 things stored in my array. And so, each of these things would be stored in consecutive locations in this plain old array of integers. Alright, so think about the kinds of things we have to do to manipulate this data structure. One thing we have to do is access the root. Can we access the root if it's stored in an array like this? Is that possible? Yeah, how do we do that?
Yeah. You just index the first, or 0.
Yeah. So root is just heap bracket 1.
Is this a common practice to implement a heap in an array?
Definitely.
Okay.
Alright, so heap bracket 1, that's the root. Can we access the last element in the heap?
Yeah, you just do root equals, or you just say last equals heap, and then heap size.
Yeah.
Bracket heap size.
Can we add a new piece of data to the next position on the heap?
Yep.
Right, so we could just do heap bracket pre-increment the heap size, and we could store a new data there. So heap size is 9, incremented to a 10. Our new data is going to go at index location 10. Well, that's just going to be this node right here.
You didn't realize you could pre-increment inside the variable that you're creating, basically, or the index that you're using.
Yeah, that's handy to be able to do.
I think I've considered doing this for a BST,
Ah, okay.
but I don't know if it would work out super well.
It's not bad for a BST either.
Yeah, and you could, let's say you wanted to make a new binary search tree implemented into an array. You would just declare, I don't know, how many children times log base 2 to the n, right? Of how many rows you want.
Yeah. And we could reallocate an array and copy this over if we needed a bigger array.
And then you wouldn't need to walk the pointer back and forth across a memory structure, right?
Well, you'd still need to pass around, the address of this array. But that's just a pointer. That's not a whole lot of real estate to move around. But we do need to move from a node to its children, right? To be able to move down the tree. And if our node structure has left and right pointers, we just say, current node arrow left, and that's the address of the left child. But how do we move down our nodes in this kind of structure when our data is stored in an array, when we don't have pointers to the left and right side? Is there a way to move from a node to its children?
Well, you could. Basically, that's just add 2, right? Or it could be
2 to the n row, I guess.
Well, suppose we're at node 1. What's the index of its left child?
2,
If we're at node 2, what's the index of its left child?
4.
If we're at node 3, what's the index of the left?
6.
All right, node 5.
Oh, 10. Oh, so it'd be 2n basically,
Mm-hmm.
right? So 2 times the index.
Yep, 2 times the index, that gives you the left child. What about the right child?
2 times plus 1.
Yeah, 2 times the index plus 1. So there's some really simple calculations to find your children in this structure. And when we want to downheap, for example, we would take the last node, right, which is heap bracket heap size, copy that into element 1, and then we have to compare it to both children. Well, the children will be elements 2 and 3. If we need to swap with element 3, because that's the biggest, we just swap elements 1 and 3. And now element 3 we need to compare to the children. Well, that's going to be 2 times 3 is 6, plus 1 is 7. So we find the largest of these compared to node 3. If we have to swap, we swap those and we continue. And it's just a little while loop. And inside that loop we basically do this simple index arithmetic, and it lets us move down the heap.
This would have been a really cool project to do.
Yeah, I'm going to do this next year, I think.
I want to try it too, but the thing I'm most curious about here is where the performance gains, if there are any at all, from moving to like a memory link structure to just, contiguous allocation like this.
As far as the implementation with an array versus, dynamic nodes, I don't think there's a difference in order of complexity, except that if you do this with nodes, we don't really have an easy way to find, the last node. Right? We would need to basically explore, everything, find the height of the tree, and explore all of those nodes, right? I mean, there's nothing about a binary search tree or a binary tree that tells us where that last node is. Now, if we know how many nodes are in the tree, if we know there's 10 nodes, we can play some tricks, right? So
I bet if you were to implement this into a class, per se, and you had maybe a pointer to the root and a pointer to the last, you'd have everything you needed. And then you might save a lot of memory for every node having, a set of pointers, right? Maybe it has 2 pointers, 16 bytes per node, and then you just don't have to have that, right?
Right. Although if we have a pointer to 10 and then we remove 10, we'd need to change our pointer to point to 9. And it's not totally clear how to do that. You need to hop up 2 nodes and then hop down left and right. And you'd almost need to have a second structure that maybe stores, these things in some kind of queue or something. But I think there's something else we could do. This is a sidebar now. Now I'm indexing from 0 instead of 1, but that's just an offset. Let's see. Here we go. So I think maybe the binary representation of an integer tells you how to get to that node in this kind of structure. Where 0 means left and 1 means right. So if we start here, right, that's our 1, 0, 1. If we start here, we want to go right, left. That gets us to 1, 1, 0. If we go right, right, that gets us to 1, 1, 1. If we go left, left, that gets us to 1, 0, 0. And so you might be able to find a path to your last node by looking at the bits that make up this integer and using that to control your movement from the root, left or right. So you could probably do something like that and get to your last node efficiently, as long as you keep track of how many nodes you have, and that's an easy metric to track.
And you could navigate via bit shifting. That's cool.
Yeah, that would be neat.
That would be even more fun to try.
Go for it.
I will.
Awesome. All right, what about our parent? Suppose we're at a node, because, if we're upheaping, we need to look at our parent. So how do we find the index of our parent by using our current index?
Well, that depends if you knew that the node was right or left of its parent, right? Because you could do like the index of the operation to get from the parent to the children, but you'd need to know if you were left of the parent or right of the parent.
But it's even or odd, it looks like.
Looks like it's even or odd. Odd is right, even is left.
Oh, yeah.
Yeah, so if you just divide it by 2, and then I guess you can minus 1 if it's odd, or plus, or
So if it's odd, you could subtract 1 and divide by 2. If it's even, you divide by 2. But if you work with integers and index is odd, this will do index minus 1 over 2. So node 7 divided by 2 is 3.5. That'll come out to 3. Node 6 divided by 2 will also come out to 3. So as long as you're doing integers, all you have to do is take your index, divide by 2. And there's your parents.
Or you could modulate and then subtract the remainder,
Mm-hmm.
I think, right?
And you could subtract your moduli mod 2 and then divide by 2. So again, pretty straightforward index arithmetic. And it lets us move up the heap as well as down. We can find the first thing, we can find the last thing. And that's all you need to do to do any of the heap things that we've talked about.
It's funny, this almost feels like cheating.
Yay!
It seems like it'd be much easier. Yeah, it seems like it'd be much easier than some of the other stuff that we've done.
Yeah. So in past years, for PA1, I've actually had people implement a linked list using an array. And we don't talk about pointers or mallocs or anything. We just use a plain old array and we build a linked list out of it. And that seems to be useful for understanding linked lists. But unfortunately, it makes it really hard for most students to make the transition to doing dynamic memory. Because it kind of like, I don't know. The first time I did that, it was great. The last time I did it, which was last year, it seemed to sort of get people in a different mindset where they thought everything was related to this array. And so I didn't do it this year. But yeah, arrays are sometimes underappreciated. The other comment I'll make, since we're talking about arrays, there's one really, really big array in everybody's program, in everybody's computer right now. It's main memory. And if you've got 16 gig of main memory, that's really just an array of 16 billion bytes. And a pointer is nothing more than an index into that array. So if I have a pointer with some value and I say star pointer, all I'm doing is saying, hey, tell me what's at element such and such in my memory array. And it just goes to that location and pulls out whatever's in that spot.
So who allocates that memory? Is that Windows or iOS that says this is the array, this is what the main memory does?
Well, it's not really treated like an array by the system, but conceptually we could think of it that way.
I've heard that, you can use different memory managers for languages like C and C++. Like, for example, you just have the operating system handle it for you, but for things like video games, per se, sometimes You
Mm-hmm.
can't allocate stuff fast enough, but the operating system will you allocate enough so you can have other things managed.
Right, right. And I mean, you could in C, you could do something like this. Make a character array called pointer, initialize it to 0. And now if I say pointer bracket loc, this will give me the contents of the byte stored at this memory address in my main memory. And so these used to be called peek functions. And if you want to see what's stored at location 10,000, all I have to do is say pointer bracket 10,000, and that'll give me the character that's stored at that location in my memory. So I can re-envision the main memory of my entire computer as an array like this. And it's not as fun as it could be because we've got virtual memory. So my location 200 is different from your location 200. I'm not actually looking at physical memory addresses because there's this whole virtual memory map that sits in between me and the main memory. But it's still potentially an interesting thing to play with.
I don't think you're allowed to do it in most cases now because it's, pretty insecure to do that, right?
You can still do it as long as you put it in a location that you have access to. So like, 6005F8 or whatever it is that always comes up when you go into GDB and you look at the address of your local variables, right? Well, I could do this in my main program and it would give me that same value. Or 7FFFFFFE532 or 30 or whatever, right? You could still do that. The compiler might not like it, but that's okay.
I think we saw this earlier in the term that GCC on both my WSL machine and your native machine there like to pick the same spots for peak.
Yeah. Which is kind of interesting. Well, WSL is supposed to be Ubuntu, as far as I know. It's like the standard kernel and the standard distro.
You can use other kernels. I've used Debian also. I think there's one for Arch. Any flavor you like, I think you can load in there.
Oh, cool. Awesome.
You have to say, my overall understanding of pointers from this term too have been, way better than I've seen prior.
Awesome.
Like, they used to terrify me. Now I love implementing them when I can.
Excellent. Yeah, that's one of the goals here is to get pointers to where they make more sense. So that's great. All right, let's talk about the final a little bit. So, dynamic memory on PA3. Oh, cool, awesome. Yeah, dynamic memory, another aspect of pointers. That's definitely a goal here. All right, final exam. So, your exam will be on Thursday. I think this is my first Thursday exam ever. So it's Thursday, March 17th, 1 o'clock to 2:50, plus, extra time if you have an extended time allowance. And you got to take it during that time. You can't just choose when to take it on Thursday. It's during those scheduled times, which is our regular class time. And mechanically, logistically, it's going to be similar to the midterm in that you'll download a file. The file will list a bunch of questions. You'll write out answers to those questions and then upload a scan of those answers as a PDF. And that'll be your submission to Canvas. If you have an extended... Go ahead.
Using the app on the phone, like taking pictures with the scanning apps, those are okay, right? I'm not at home right now.
Did you do it on the midterm?
I didn't, no.
Okay.
I used my scanner at home.
You might want to do a test load well before next Thursday. Just do a test and you can send it to me if you want.
Okay. Yeah, it's just, I think it takes pictures, and then it uploads it as a PDF, and I can email it to myself. And
That sounds perfect.
that way.
Yeah, as long as the quality is okay, that should be fine.
Yeah, I've used it for other classes for their finals and midterms, but I didn't know. I wanted to make sure before I do that.
Okay.
Find out on Thursday. Yeah.
Yeah, the only concern would be legibility, and as long as I can read it, you're fine.
Okay, yeah, it's pretty high quality. So.
Okay, cool.
Thanks.
Yeah. All right, so your page allotment is 6 double-sided pages of notes or 12 single-sided pages, up to an A4 size page. So you got plenty of note page budget. My goal is not to limit you on how many pages you can have. My goal is to put in a number so that so that there's some guidance there. But your notes have to be printed or written, right? They have to be physical notes. I don't want you doing anything online other than downloading the exam or reading the exam in Canvas, using whatever tool you have to use to make a PDF and then uploading the PDF.
So if we're having the final Thursday, are we having Tuesday class?
No classes next week. Next week is all exam week.
Okay.
And I don't know why it ended up on a Thursday. I think because it's 1 o'clock. So I think Tuesday, Thursday classes at even hours, I think, are on Tuesday. And then the ones at odd hours are on Thursday. And if you have an extended time allowance, Canvas will tell you that your submission is late. Don't worry about it, right? I've got notes on who has what deadlines, and I'll grade it accordingly. And if you don't upload it on time, Canvas automatically gives you a 0. Don't worry about that, right? Guaranteed, if you got a 0 on the exam, there would be tons of feedback, right? Or you just didn't show up for it, and there'd be feedback anyway. So don't panic with Canvas's sort of quirks. And so yeah, 6 pages double-sided, 12 pages single-sided, your choice.
Could you say that one more time? Why are we not supposed to panic?
Sorry. If you have an extended time allowance, right?
Okay.
Canvas doesn't know about that. So if you don't turn it in by 2:50, Canvas records a 0. And you upload your exam and you go to look and it says you got a 0, right? And that's a panic moment, so don't panic.
Gotcha.
Okay. Sorry, I didn't mean to panic you now.
It's okay.
Okay. All right. And as far as structure of the exam, so there'll be some programming questions. And as usual, sometimes I might ask you to write a program, I might ask you to write a function, I might ask you to write a few lines of code. So be sure what it is I'm asking for, and if you're not sure, ask me. And so I recommend being logged into Zoom, and I'll be in Zoom during the exam time. I'll keep my microphone muted for the most part, but if there's a correction or clarification, I'll announce it in Zoom. And if there's something you're not sure about, you can send me a message and ask me. All right, and so there'll be some programming questions, long or short. There'll probably be some short answer, fill in the blank, multiple choice kinds of questions, and I have not written this yet, and it's going to be a different exam from other exams I've done. So I don't know how many questions it will be or how many programming questions or things like that, but I'll try to set it so it's doable in an hour and 50 minutes. But you can probably expect some questions other than just write some code. So explain what a sentinel node is used for, or give name 2 differences between chaining and probing in dealing with hash table collisions, or questions like that. So we'll see what I come up with.
And just to be on the safe side, chaining meaning like setting up a linked list and then working down the linked list, and probing being see if there's a good spot, and if not, go to the next one.
Yeah, exactly. You got it.
Okay. it's been a while since we're doing hash functions, so.
It's been even longer since we did linked lists, so.
That's true.
So yeah, preparation, right? Definitely go back and look at your programming assignments. Those are really good practice. And if you finished an assignment and you weren't feeling like you really understood it, or it worked, and you kind of like held your breath until it got graded, and then you were like, oh, I'm glad it didn't break, right? Go back into your code and see if you can, solidify your understanding. See if the stuff that you felt iffy about, you can rework and feel better about. You'd like to go into this with a pretty solid understanding of linked lists, stacks, queues, binary search trees, hashes, dynamic programming, right? The stuff we've done in the programming assignments. That's all good material.
There too, right?
There'll probably be a lot of recursion because most of what we've done has been recursive. The linked list stuff being kind of an exception. And so yeah, I don't expect people to have a completely comfortable relationship with recursion yet, but certainly after PA5, it should be making more sense now. Even if it's kind of quirky. But I mean, knapsack problem was all about recursion, right? There was really no other way to do it. So think of your solution in terms of solutions to smaller problems, and then use those to get the solution to the big problem. Well, that's pretty much what recursion always is. It's solve the smaller problems and then use those to answer the bigger questions. Alright, so I posted a study guide yesterday. We worked this out in the Wednesday class, and then I stuck a PDF up here. And this is not necessarily 100% inclusive, and it's probably got a lot of things on here that you won't see on the exam, but as kind of a approximate, superset of what we've been doing this quarter. Here it is for what it's worth. So I can just kind of go through this from start to end, and we'll take a break in a few minutes. But if there's particular questions about material that you want to ask about first, I'd rather start with questions that people have right now than like just start talking about this and then in an hour somebody's like, oh yeah, what about this? So I don't know if you've had a chance to look at this already.
I would imagine we're probably not going to see anything with doubly linked lists, right? Except for maybe like a concept question.
There could be a concept question, or I could give you a piece of code that uses doubly linked lists and ask you questions, or I could ask you to implement something that deals with a structure with back pointers. But I don't expect that you've already done this. But even if you've never coded a particular algorithm for a particular structure, you probably would be able to if I gave you enough information. So there could be questions related to that.
Well, the doubly linked list, the only difference is instead of having a pointer to the next node, it has a pointer to the back and the one behind it too, right?
Right. So you have a pair of pointers. So you got data, and you got next, and you got previous, and this goes forward and this goes back. Got invisible ink.
We're not seeing that.
Yeah. There we go. So yeah, there's a node and it's got a pair of pointers. So well, let's go ahead and take a 5-minute break, and you can eyeball this during break, and then when we come back around 2 o'clock, if there's something you want to talk about up front, we can start with that. Otherwise, we'll just run through it in order. So I can't fit this whole thing on here, but yeah, maybe I can. but you can also look at it on canvas. Alright, so I'll be back in about 5 minutes. I want another Coke, but I won't. Your mustard made me think of pretzels.
Oh, how interesting.
Have you put out walnuts?
Nope.
I would do this.
Excellent.
It's in my memory. Memory of me?
What?
Did it do this in memory of me or do this in my memory? Remembrance of
In memory of me.
Remembrance or memory?
In memory of me, but I went to hippie church, so you know.
So they said dude after?
Yeah.
Okay. I don't know if this is Mirror or the Rabbit.
Mirror the rabbit. Wait, what's going on there? Oh! I was looking at the middle. I'm like, somebody drew a picture of it. That's the rabbit. That's the rabbit. Like, nah. Well, actually, that could have been Mara. Well, you know what she said? She
What?
just wants them for her eyes.
Oh.
Yeah.
This is all super bonus content on the recording.
Okay. Yep.
2 seconds.
I'll definitely desk that one.
Okay, nice squirrel. Alright, we're back. Alright, any questions before we just kind of go through this? Alright, well, so starting from the beginning, right, structures, so you should understand that structures are a way of taking multiple pieces of data and sort of grouping them together. And they may or may not be related to pointers, they may or may not be related to mallocing memory, right? So if I have a struct...
I had a question about that actually.
Yeah, go ahead.
Talk about structs. Why are structs always default passed by value rather than, well, like, I've seen this before, but I don't quite understand why.
Everything is passed by value in C. Right, that's the only option for passing arguments to functions is by value. And so if I have, you know, a structure with some name, and I declare a variable of that type, struct name, and I call a function, and I say function of, you know, that variable, I pass the value of that variable, which means, you know, all the stuff in that structure gets passed. But often what we do is we declare things to be pointers to structures, and then when we pass, you know, variable to a function, what we're passing is the address of that structure. And that's probably the more common thing that we do with structures when we pass them around, is we pass their addresses, so we pass references rather than values.
I think let me rephrase that question a little bit better.
Okay.
If you were to pass a string in an array, you're always passing a pointer, no matter what, right? You're passing a pointer to the first element, but if you just pass in a non-pointer struct to a function, is it actually just passing all of that memory, or a pointer to the beginning of that?
It's copying all that memory and passing it.
Okay.
Yeah. The reason that strings get passed by address is because they're actually declared as pointers to a character. And what we actually pass is the value of this variable, which is the value of that memory address, right? The number that represents the location in memory. That's the thing that gets passed by value. And it's still passed by value. It's just that we use that value as a memory address. But yeah, if I pass a name of a variable that's just a struct, it will pass all the fields of that as well, which is pretty cool. But when we declare a structure and it's supposed to contain a reference to another one of these same structures, we have to use pointers. Otherwise, the poor compiler goes down the rabbit hole and never comes out. We can't say that a node actually contains a node, right? Because that node inside would have to contain another node, and that would have to contain another node, and so on. You get inception. So we can say instead it's got the address of a node. Well, that's fine. An address is just 8 bytes. No problem. I don't need to know that it's the address of a node. It just has to be an address. And so that's one of the reasons that we tend to use pointers to structures when we build up linked lists, trees, things like that. The other reason is that, you know, we might have a node for a trie that contains 26 pointers and all this other stuff. If we pass the address of a node, it's still just 8 bytes. It's a really small thing to pass instead of, you know, the actual contents of a very large structure.
Sure.
So, let's see. Pointers to structures versus actual structures. Allocating memory for structures, that's a malloc. Accessing fields. So if you have a structure with some name, and it's got, you know, a field 1 and a field 2 and so on, and you do struct name variable, you access these fields by saying variable dot field 1, variable dot field 2, and so on. If you have a struct name star pointer, you access the fields with an arrow instead of a dot. So use a period to access a field if this is actually a structure. Use an arrow to access a field if this is a pointer to a structure. That's the whole difference there. And then arrays of structures, well, you got to play with these in PA5 and also a little bit with hash tables, right? I could have a struct name, you know, data bracket 100, and now if I say data bracket I, that is a struct name, and so if I want to access a field, it would be data bracket I dot F1, for example. And so arrays of structures work just like arrays of ints or characters or anything else. You declare it the same way: type, variable name, bracket size, and you access an element by just bracket index. Linked lists. So linked lists were our response to the fact that manipulating arrays can be very expensive. In particular, trying to insert something in the beginning of an array requires you to move everything after that location in the array down one spot to make space. And so whereas inserting into and deleting from arrays could be expensive, we came up with a linked list where we basically have nodes pointing to one another. And so if you want to insert something between two nodes, you just make a new node and you point to that instead of the thing you used to point to. And so we improve the order with which we can insert or delete something in the middle of a linked list. And so that's, you know, list versus arrays, order of complexity. So arrays tend to be order n to do things. Linked lists, if you know where you want to do the operation, it's typically order 1. On the other hand, a sorted array is very fast to search. That's order log n, because you can divide and conquer. You can play high-low, and you can't do that with a linked list. Sentinel nodes are a convenience that we use to not have to deal with a null list. So a sentinel node is always present, and if you delete all the nodes from a linked list, you still have a sentinel. And it means we don't have to deal with a list possibly being null, like if you delete the first thing. And we don't change the handle to the list by inserting in the beginning. The handle is always a sentinel node. So it's purely a convenience. And then searching, traversing, inserting, deleting, all of these things work the same way. You start at the first node, which is the sentinel. You follow the pointers from node to node until you get to where you want to be, and then you do what you want to do. But it's always this process of starting at the beginning and following the nodes. And that's why lists are fairly inefficient. They're order n to do most of these operations, because it takes that many steps to get to the point we're interested in. W linked list, we mentioned, is just, you know, a node with pointers forward and backwards. Asterisk and ampersand, so these relate to pointers. This gives us something that points to a variable, so it returns a reference to a variable or the address of a variable. This dereferences a pointer, so it gives us the thing that a pointer points to. So this says, you know, go to a memory location. This says, give me the memory address of something. And then period and arrow, that refers to, you know, accessing fields of structures, whether it's an actual structure or a pointer to a structure. We talked about pass by value versus reference. We always pass by value in C, but sometimes we pass by value the address of something. For example, when we call scan, we pass the address of an integer so that the scan function can change what's at that address. So it looks like it passes back, you know, a new value of the integer. but it's really just a mechanism we're using to trick it into changing something for us.
Can I ask you a quick question regarding arrays and lists?
Mm-hmm.
So, would you say that each of them obviously have their merits? Because like arrays would be easier to find something you're looking for at a certain index, right?
Right.
Whereas lists, you kind of go through, but then to add and delete stuff from an array would be quite inefficient, whereas lists are very efficient. So,
Yep.
would you say it's just depending on the task that you're doing?
Yeah, exactly.
The manipulation you're trying to do? Okay.
So like the heap implementation that we went through earlier in class, that would be terrible to do with a linked list, right? Because you're at a node, you'd have to know that this was the 5th thing in the list, and if you wanted its left child, you'd have to move down 5 spots in the list, right? And it's you know, a really poor approximation for an array. An array, you know, the ability to say, give me element 19,207, it takes, you know, a fixed amount of time to get to that element because we know exactly where that element is stored in memory. So yeah, accessing a particular element in an array is super efficient, order 1, but then squeezing something into the beginning takes order n. And then since, you know, each of those has pros and cons, we sort of, you know, move on to binary trees, and binary trees give us the best of all the worlds. All right. Yeah. So, you know, malloc for allocating space, and if you have a pointer to something, it's usually got to have memory to point to, unless you're passing it in as an argument to a function or something. You're going to want to use malloc to get space for it. Malloc often gets used with size of, and, you know, cardinal rule I'll give you for size of, don't ever do size of a variable. Do size of a type of variable only. If you want size of an array, do the size of the array the length of the array times the size of whatever type of thing is being stored in that array. C++ uses ampersands for function arguments instead of star. That's fun. I didn't realize that either. Alright, so malloc for allocating space, free for releasing space, valgrind to let you know how you did. So you can valgrind your program, it'll tell you if you've got memory leaks or other memory issues. GDB, so you should be pretty comfortable with GDB at this point, at least for basic use. So compiling with GDB support, running GDB, setting breakpoints, saying step, saying next, saying print, maybe saying examine to look at memory, and continue to keep running until a breakpoint. Maybe playing with watch points. So these things should be fairly familiar to you at this point, and they're things that you're going to keep using throughout school and beyond. So it's good stuff to stay up to date on. Makefiles, you've done makefiles for all of your assignments, so I think people are pretty good with makefiles now. I don't think I saw any major makefile issues on PA5. So that's good, but you know, review your basic makefile. At least include a basic makefile on your note sheet in case I ask you to, you know, write a makefile for some project. And just kind of like go through and make sure you know what each of the pieces of a makefile are. It's basically a file of recipes, and it's a pair of lines, a dependency and a recipe for satisfying the dependency. Abstract data types. This was the idea we've been going back to throughout, which is that most of the data structures we've talked about we can think of at 2 different levels. We can think of it abstractly, or we can think of it in terms of how we implement it. So a stack is something that you can push something onto. You can pop off the last thing pushed, and it remembers things in the reverse order from which they were added. That's an abstract view of a stack. Implementing a stack with a linked list where you push by inserting in the beginning and you pop by removing the thing right after the sentinel node, that's an implementation view of a stack. Implementing a stack with an array and an index called stack pointer that you increment before you copy, that's an implementation view of a stack. right? And we're very often interested in the abstract view of a data structure like a stack. Or a queue, you can add, you can remove, you can see if it's empty, you can see if it's full. And so most of the structures you've created, you made a series of functions for interacting with your structure. And those functions mostly looked at the structure abstractly. So to initialize a linked list, you did not ask the main program to declare a struct node pointer and then call malloc with size of struct node, etc., etc. You just said init, right? Make a struct node pointer called, list and set it equal to init. For a tree, you just set something equal to null to initialize it. And then those functions that you call init, add, traverse, delete, and so on, those deal with the low-level details of how the thing is actually implemented. So there's the abstract view of a data type, and that's going to be important in 223 also. Lots of recursion, so most of the good stuff we've been doing has been recursive. Increasingly so when we got to trees, and then to an extreme with a knapsack problem. And you want to be pretty comfortable with if somebody gives you a recursive definition, right, believing that works and having some idea how you would code that. So when I tell you the height of a tree is 1 plus the height of the tallest subtree, that's a recursive definition. Take the tree on the left, find its height. Take the tree on the right, find its height. Take the largest of those, add 1, that's the height of the tree. And you usually need a base case. In this case, if the tree is empty, return -1. That's the height of a null tree. And so all these recursive functions, we're trying to evaluate a function with some value for an argument. And instead of doing that directly, we evaluate the function for different values of the argument, and we combine the results of those calculations. And we can think of lots of things recursively that we haven't done yet. One example is string length. So here's a way to find the length of a string. If our character begins with a null terminator, let's return 0. The string is empty. Otherwise, return 1 plus the length of, and I'll do ampersand str bracket 1. This is just a string that begins with the second character of str. And I'll find its length and I'll add 1 to that, and that's what I'll return. And there's a recursive string length function. So we can start to think of lots of algorithms perhaps as being recursive, and that opens up some new ways to solve problems. Alright, we talked about stacks and queues. You did some assignments on this. So stacks we can push and pop. There's an overflow when you push too much, underflow when you try to pop too much. You implemented it with a linked list. In your programming assignment, you can also implement with an array. So you have an array that you store your stack entries in, and you have a stack pointer that basically indexes that array. And as you push, you bump up that array, and as you pop, you bump it down. And the details of that, right, there's different options. Which way do you move the stack pointer when you push or pop, and so on and so forth. Queues, exactly the same setup. So you can insert and remove. They can be full, they can be empty. You implemented these with linked lists in a programming assignment. But here you did your insert at one end of the list, and you remove from the other end of the list. And if you implement this with an array, you need a pair of pointers. One to say where should I insert, and then another to say where should I remove from. And so this gets us into the idea of a circular array, so that if your array falls off the end, it may be possible to wrap it back around to the beginning if there's still space in the queue. Alright, hashes. You did a hash assignment, but it's probably been a long time ago. So here's the idea of a hash. You have a plain old array, and you'd like to be able to index this not just with integers, but with, something like a string. And C does not support that. I can't say array bracket quote haha. Get a syntax error. So instead, what we do is we take our string and we run it into some function that we call a hash function, and it gives us out an integer, and that tells us where we should store our data associated with this key. So it's this intermediate, the hash function is an intermediate step that basically takes the thing we want to use as an array and says, okay, store that here, store it there, store it there.
Out of curiosity, this kind of also kind of off. In Bash, when we did this last quarter, we did associative arrays. Is that basically just a built-in hash function? Then?
Yeah.
Oh, that's cool.
And it's built in, so it hides from us the fact that this hash function might be taking place. But in Bash, we actually say array bracket quote, and it will do the right thing. But it's probably using a hash function and mapping this to an integer inside. But it could be doing something different. And so again, as an abstract data type, a hash is something we can go in with a key, we can get a piece of data. And how that's happening, well, that's hidden from us, and that's okay. It doesn't change our understanding of how to use this, just how it was created. C does not support operator overloading. Fortunately or unfortunately, depending on who you ask to. But it's got a good macro facility, and it has a nice preprocessor, so you can almost do similar things. And you could always write your own C preprocessor that replaces, an asterisk with a call to your multiply function or something.
Do you do like a macro in a context or something?
Like what?
I don't know, let's say I make a macro if I call a hash function index this thing here. And if I made a call to that and it's followed by 2 square brackets, take the argument inside those square brackets and do something.
I don't think it's that sophisticated. But I know people who have written preprocessors that get run before the compiler gets run that will do some really quirky synthesis of C code on the fly based on things like that. I'm not naming any names, but I've heard that people do this sometimes.
That is cool. You could make your own preprocessor if you really wanted to.
Absolutely. And C is such a symmetric language, it's basically function calls that it's not too bad to try to do that.
Hell, you could do that for any language, come to think of it.
You could. The only trick is, some languages are more complex. The structure of C is so sort of simple that that it kind of makes it easier to do stuff like that. And yeah, so you can get into things like this, that this set of instructions generates an entire C program, right? Even though it just looks like, a bunch of calls to this set TT. Well, when I run this through my compiler, it adds some header to it, and it adds some trailer to it, and it puts this in the middle, and it defines these macros and these symbols and so on and so forth. And that's totally legit to do, and especially if you're in something like Unix, where you can call a compiler from inside a script, right? And you can put files together inside your script and so on and so forth. This is all pretty straightforward to do, and it's one reason why so much development is done under a Unix environment, because it just lends itself to that. as opposed to, you know, having a robotic arm that moves your mouse around and clicks on the compile button in an IDE or something, which would also be cool in its own way.
It's funny because since we've been doing so much C, I've found myself complaining that other local languages don't have a preprocessor.
Yeah.
It's been stopping me from making my own, right?
Right, exactly.
It's a good epiphany.
Awesome. All right, so hashes. The whole game is, you know, taking whatever you want your keys to be and using that to get you somewhere in an array. And the challenge comes in when you have, say, two different keys that take you to the same spot. So that's a collision. And we talked about two main ways to deal with collisions: chaining and probing. So chaining is what you did in your programming assignment, and it basically said, hey, instead of storing my data here, I'm going to store a pointer to a linked list. And I'm going to store my data in a linked list, and every piece of data that's associated with something right here, I'm just going to add a new node and store my data in that node. And so we can, you know, have multiple things that all hash to the same location, lots of collisions, and we can still store them all. Because we're not actually storing them in this array, we're storing them in the list pointed to by this array. And another way to think of this is, you know, we could just take all our data and store it in a linked list, but that's, you know, a big long linked list is inefficient. So instead we have, you know, maybe 1,000 linked lists, and the hash function just tells us, hey, if you're looking for something associated with this, check linked list 17. And it gives us, you know, the exact linked list, which will be short, hopefully, to look through to find this key and its corresponding data.
The hash table, that could be considered an array, right, or a type of array?
It usually is an array, right? So it's an array of sentinel nodes, example in our programming assignment, or it could be, you know, an array that stores directly the data that we're storing, and in that case we handle collisions using what's called probing. And so probing basically says, you know, if I hash something and it wants to store that data in this spot in my array, but that spot's already in use, just hash it again. Use a different hash function. And so we usually have two arguments to our hash function. We have the key we want to hash, but then we'll have something we can think of as a probe number. And so I'll hash my key with a probe of 0, but if that doesn't work for me, if that spot's already in use, I'll hash again with a probe of 1. And if that spot's already in use, I'll hash again with a probe of 2, and maybe that spot's open. And so that's where I'll store my data associated with that key. And probing has advantages and disadvantages. One of the complications is we need to, you know, keep track of where we've stored things, so that, for example, if I delete this and then I look for a key that originally hashed to here, I know, hey, it might have had a collision when I got here. Let's hash again, see if it's stored at another location. So there's implementation complexities. All right, AVL trees. So, binary trees. So binary search trees, right? So you've done code on this also. And, you know, main property of a binary search tree is this question of left versus right children. So typically we have a root node, stuff to the left will be smaller, stuff to the right will be bigger. And because of this property, we can do things like, if we want to search for something in a tree, if we're searching for something smaller than the root, we can ignore the root and everything to the right of the root. And we can just look in this subtree to the left, maybe a single node, maybe 1,000 nodes, but we can throw away all of this stuff. And so binary search trees tend to be very efficient and very recursive in our algorithms. So even though we could, you know, start from the root and just move down left or right at each point, we can usually think of our algorithms recursively. And so if I'm searching for a number, if it's bigger than 40, I'm just going to search 40 arrow right, and whatever that search returns, that's what I'll return. If I want to insert something and I want to insert something smaller than 40, I'll just insert it into this left subtree by making a recursive call to insert. So our BSTs tend to invite a lot of recursive algorithms. And things like depth and height. So depth of a node is the number of hops from the root to the node. Height of a tree is the depth of the deepest node. So those are related, but height is a property of the tree, depth is a property of a node. And we can define those recursively, or we can define height recursively. Balance is sort of how well the tree is evened out between left and right. And remember, there's three things that have to be true for a tree to be balanced. The left subtree has to be balanced, the right subtree has to be balanced, and the heights of these have to be within 1 of each other. And so that was, part of your output function for a programming assignment, was to report on the height and the balance of the tree. 3 traversal orders, so 3 depth first orders, which we call pre-order, in order, and post order. The pre, in, and post prefix referring to where in this traversal we print out the root node. So with a pre-order, we print the root node first, then we traverse the left tree, then we traverse the right tree. With an in order, we traverse the left side, we print the root node, we traverse the right side. And with a post order, we traverse the left side, then traverse the right side, and then print out the root value. And these are all depth first, in that they move down and up a little and down and up a little and down and up a little. And we're going to print out everything over here on the left before we do anything on the right. So they go deep first and they slowly move up and move over to the right. But there's also a breadth first order, or a breadth first search, which moves across each level like this. And we looked briefly at how we could code this using a queue. And it turns out we can code these traversals, these depth first traversals, using a stack. And we can code breadth first using a queue. And they're kind of duals to each other. But when we want to do these depth first, we usually just use recursion. Right? So to do NLR on a tree, do NLR on the left. Or print the root node, do NLR on the left, and then do NLR on the right. But we could implement it with a stack also. And then searching, inserting, deleting, these are done recursively. And delete is sort of the trickiest. If we want to delete from a tree and the value we're deleting is smaller than the root, that's easy. Just delete from the subtree and then set this thing to point to that new subtree on the left. The tricky part of a delete algorithm is deleting the root. And that's where we get into, having to actually do some work. Whereas, searching, if we need to search the root, that's easy. If the root equals what we're looking for, we found it. If it doesn't, we didn't. But deleting the root is where we get into some potential complications. And so the algorithm that we used for our assignment was we're going to replace the root with the largest thing from the left subtree. We could have replaced it with the smallest thing from the right subtree. Either of those will work, in the sense that the search order of the tree will be unchanged. It'll still be a binary search tree. So if we do the smallest node from the right subtree, right, that would mean move down as far to the left as possible. That would be this node here. If we do the largest thing from the left subtree, which was what we did, we'd go into the left subtree and we try to go as far to the right as possible. Well, if there's nothing to the right, this is the largest thing. This is going to be the new root of the tree. But if there's stuff over here, right, then perhaps this will be the largest thing in the tree, and so this would become the new root. And then it's going to orphan some children, so those will get adopted by this node's parent, and it'll adopt it on the right. So there's all these details, but the basic idea, the basic goal is replace this with the largest thing on the left. And if there's nothing on the left, deleting the root is easy. Just, free that and say, hey, this is the new root. So you don't have to move anything at all. All right, AVL trees, we have not coded anything for, but we talked about them. So we worked with this picture. And if I ask you to do anything with tree balancing, I'll give you these pictures on the exam, so you don't need these in your notes. But the two concepts were, one, calculating the balance factor of a node. And remember, balance factor is the height of the left subtree minus the height of the right subtree. And it's not recursive. We don't calculate balance factor by using balance factor. So if we have a tree like this, this has a balance factor of 0, 0, 0, 0. This has a balance factor, well, this tree has a height of 0, this tree has a height of 1, this has a balance factor of -1. Right? And don't just say, 0 minus 0 is 0. We're not subtracting balance factors, we're subtracting heights. So the balance factor here is the height of the left subtree, which is 1 node, minus the height of the right subtree, which is those 3 nodes. So 0 minus 1 is -1. And so if your tree was balanced before you inserted or deleted something, after you do the insertion, you can check the balance factors, and if you find a plus or minus 2, you have an unbalanced tree. And so, for example, if we come here and we find a balance factor of 2, and the left child has a balance factor of -1, that's what we call the left-right case. And you need to make an adjustment. You need to do a rotation to change this into a left-left case, and then change that into a balanced tree. And the goal is to, make these adjustments each time we change the tree, so the tree is always balanced. The hope being that the height of the tree is close to the logarithm of the number of nodes, so that when we ask, how long does it take to search or insert or delete, it really is close to log n. And those log n orders only apply if the tree is close to balanced. If our tree looks like this, where we have 1,000 nodes, the search time for this tree is about 1,000 operations, right? But log of 1,000 is only 10, so log n would say we could find something in this tree with 10 operations, but in practice it could take 1,000. So if this tree was balanced, it would look like this, and it would have a height of 10. So starting from the root, you make 10 hops or so, and you get down to a leaf node. So balancing is related to efficiency and getting those nice log n orders of operation. All right, and then tries. Tries are these really wide trees. So we used a worksheet like this. Similar to a tree, but instead of binary, we have many children on each node. And in this case, we store a word by coming off of the appropriate pointer for each letter of the word. So if we want to store a cat, we come off the C pointer to a node. On that node, we come off the A pointer to another node. On that node, we come off the T pointer to another node. And on that node, we set the end of string marker to say, hey, there's a word that ended here. What was the word? Well, it was C-A-T. It's a cat. And so tries take a lot of memory, but they're very efficient time-wise, because we don't have to go very deep to find a word. We could have, 26 to the 10th words stored in here, and it would only take 10 operations to find a word or conclude the word's not stored.
So real quick, out of curiosity, are you, every time you go down a level, each individual element starting from A all the way down? So if you're doing cats, it's going to be the M before it gets to the end string.
So if I do cats, I would come down C-A-T down to here, but then at this node I would follow the S and come down and then have the end of string set here.
Okay.
And I wouldn't want to store cats here, because then if I wanted to store a cat, I'd have a problem.
Okay.
But you could envision a hybrid structure where you use this for, say, the first 3 letters, and then maybe instead of an end of string marker, I have a linked list of words that started with CAT, and I store those in just a list or a tree or something.
We were at the mall.
Gotcha.
It was super
Okay.
random.
All right.
She's like, oh, let's try.
All right. So main advantage of tries, very fast for storing and searching and retrieving information. And the downside is they take a lot of space because you have a lot of pointers, and a lot of those pointers are unused. All right, now we're up to PA5, dynamic programming. So 2 concepts here. The first is, a very recursive problem, something where the solution can be expressed in terms of solutions to sub-problems, but we have to solve maybe a lot of sub-problems and combine those solutions. So a knapsack that holds 100 pounds, we might have to try, 50, 60, 70 other calls to our max_val function, and then combine the results of all of those to find max_val of 100. And so it's intensely recursive, and we can speed up that recursion by doing what we call dynamic programming. And dynamic programming basically saves the value of our recursive function once we calculate it. And so the first time I ask, what will a bag of capacity 20 hold, I have to, call a bag of 18 and 17 and 15 and 12 and 3, right? But each time I call those values a max_val, each time I call max_val for those capacities, I save the result. And now if I'm trying to find max_val of 22 and I need to know max_val of 18, I don't have to work to find max_val of 18. I've already calculated it, I've stored it in memory, I just read it out of memory and return it. And so if we drew a tree about that showed the recursion and the calls being made, we're basically pruning that tree. We're lopping off a big chunk of it. All right, so and so those are the concepts of dynamic programming. This is all on the video, so you're good to go. We've mostly been reviewing, but in the beginning we talked about implementing heaps with arrays, and so that's new material. The rest has been mostly review and discussion. Some good discussions. All right, so we did the knapsack problem for a programming assignment for dynamic programming. We talked about rod cutting. I think we talked about longest common subsequence, and I just posted the code for that at someone's request. And there's other problems we can work with too, so we'll maybe talk about some of those in 223. Maybe we'll drop eggs in 223. I've never done that in there. Alright, sorting. So we started talking about sorting last week, I think. So bubble sort, insertion sort, selection sort. These are our order n² sorts. Pretty quick to code, pretty easy to implement, not very efficient for large data, but not bad for small data. You want to sort a few thousand things, any of these will work fine. You won't even notice a delay. You want to sort a billion things, these probably aren't the best ones to use. So merge sort is an n log n sort, and you basically split your list in half, sort each half, and then mix the two halves together. Mixing is efficient. You just pull off the top of each pile and put them to your output pile. And splitting the list in half is easy, and to sort each half, we use a merge sort, so it's recursive. Quick sort is the one where we have the pair of pointers, and so you have your data in no particular order to begin with. We pick one number to be our pivot, and then we start from one end and we move over until our number is bigger than our pivot, and then we start from the other end and we move over until our number is smaller than our pivot. These are now on the wrong side of each other, so we swap them, and then we continue. And when we find another pair where this is too big and this is too small, we swap them. and we continue, and eventually these two things meet each other. At that point, we swap that meet point with the pivot, and now this is the pivot in the correct location. Everything here is smaller, everything there is bigger. Now we just have to sort these two halves, and we do that with quicksort. So it's also recursive, it's also n log n, and it's fun to program. Radix sort, we sort digit by digit, and start with the least significant digit. Order them by this position, order them by this position, order them by this position, and when we're done, everything is sorted. And the only trick is, as we're sorting by, say, this digit, we have to keep things in the current order they're in, unless unless it's necessary to change them. So if we have a 300 and we have a 170, both of these end in a 0. They need to end up in the same order in our output. We can't swap those. And so the way that we went through doing this sort digit by digit was to just make multiple passes. Pull out the 0s, pull out the 1s, pull out the 2s from top to bottom, and just copy them to the output. So that was a radix sort. And then the other thing was a heap sort. And so heaps, right, we talked about a little bit today too. Max heap, min heap, two basic types. And heaps have two properties. They satisfy the heap shape, and each node satisfies the heap property, either max heap or min heap. When you want to insert, you put something into the last spot, and then you upheap. When you want to remove, you remove the root. You take the thing in the last spot, put it in the root, and then you downheap. And then heapifying means building a heap out of a set of data, and instead of adding your data and upheaping each time, you just take your data, you lay it out in the shape of a heap, and then we do this process called heapifying, which means starting from the last number in the heap, move your way towards the root, and at each point downheap. Right? See if it satisfies the heap property. If not, swap with the appropriate child, move down, and repeat. And heapifying turns out to be order n, so you can build a heap of n numbers in basically n operations. And that's super duper handy. And then implementing with an array, that's what we started with almost 2 hours ago. Alright, so this is all boilerplate things you should be prepared to do. Write code, work with pointers, dereference variables, do mallocs, do freeze, declare structure, access fields in the structure, and so on and so forth. Analyze code, modify code, make changes to it, add things to it, remove things from it, tell me things about it, that sort of stuff, including recursive code. And you may encounter recursive algorithms that we have not gone over. Don't worry if you see that, right? Just work it out. We've taken a number of recursive algorithms: tree height, tree balance, knapsack packing, things like that, and written code for them. So you may be asked to do something like that. Lists, trees, tries, hashes, stacks, queues, other data structures, right? You should understand these things. I might ask you to write code to, insert something in a list or delete something from a list. I might ask you to show me where something would get stored in a hash table, given, a particular key and a particular hash function. I might ask you to show me how this list changes if it's a stack and you push 3 things onto it, right? So concepts like that. And I may have some short answer questions, like I said. GDB, Valgrind, Makefiles, some of the tools that you've been using. So, I could give you a Makefile, ask you to make changes to it. I could ask you for some GDB instructions to do something, or stuff like that. I could ask you to do some of these sorts on a set of number, right? I might give you a set of numbers and say, show me the first pass of a quick sort, assuming that this is our pivot, or something like that. I could ask you to do operations on trees. I might give you a tree and say, insert this node, and now show me how you balance the tree. So calculate balance factors, write them next to each node, identify whether this is a right, left, etc., and then do the rotation by hand and show me the balanced tree. Stuff like that. Like I say, I haven't written the exam yet. I've been thinking about it, but I don't have anything much written down yet, so not 100% sure. But there's some ideas of things you might be asked to do. And so similar to the midterm, basically. All right.
Other to some of those algorithms that gave me a ton of trouble in PA4.
Like what?
I'll review them. Like hide it first.
Oh yeah.
That was pretty tricky.
Yeah, definitely go back and review those and try to feel good about them. They're good examples of recursion. And if you didn't code them recursively, go back and think about how you could code them recursively, because that's usually the way we're going to tackle these things. Traversals are good.
Office hour tomorrow at 8, is that right?
Tomorrow at 9 o'clock, 9 to 10.
Okay.
Yeah. And over spring break, I'll probably post a couple of office hours per week for advising and such, so you can catch me there also. But I'm not going to have any hours planned during finals week. All right. Other questions, comments, topics?
Are you still gonna post that video on the red blacks?
I have not gotten to it, but it may be something I do over spring break.
Okay.
Yeah.
I would love that.
That's code for I have to learn about red-black trees first. I know the basic concept, but I've never tried to code one, so that might be a fun thing to do over break. And yeah, I'll definitely post something if I come up with it.
Cool.
Yeah. Did I post this? Oh yeah. Yeah, I did post this. All right, other questions? All right, well, you're going to get out 7 minutes early today. So thank you everybody for the course. Thanks for your effort and attention and work in here. I appreciate what everybody's put into this, and I think people have made amazing progress in this course and in this subject, and I think it's set people up well for 223 and beyond. So don't stress too much over the final. Just go back and review your stuff and plan to come in and just show me some code and tell me about some concepts, basically. And let me know if you have questions ahead of that. Otherwise, I will see people. I might see you in a 215 final if you're in there. Otherwise, I'll see people next week. And good luck on your other exams, and I'll see you next time.
Yeah, thank you. Thanks for everything.
Yeah, you're welcome.
Thank you so much.